Okay, so welcome. As we go over what's going to be on test three. Test three is probably the longest of the tests. Typically seems like it takes the longest amount of time. What you really want to be cautious about is the problems with absolute max and min, increasing, decreasing, relative max and min, concavity, and points of inflection are all very similar problems. And so you want to uh, make sure you realize what you're doing in a given problem. So I just want to go over some of the things we've gone through in the notes to kind of give you a heads up or an idea of what to look for problem-wise on your exam. So the first topic we talked about was finding absolute max and min. So if you go to the 4.1 notes, starting around page 6 is where we actually have our examples. Right, remember to find the absolute max or min. We find the derivative, figure out when it is 0 or undefined. We then evaluate our original function at the endpoints and at any of those critical points. Whichever value turns out to be numerically the biggest, that'll be our absolute max on the interval. Whatever value turns out to be the smallest numerically will be our absolute minimum on the interval. So here we just dealt with a polynomial in this example. Here we're doing with a slightly bigger polynomial. So again, we went through the process of finding the derivative and eventually set it equal to 0 here. And we got 3 critical points in the interval, -4 to 4. So we evaluate not just at -4 and 4, the two endpoints, but also at the inner values. And again, whichever numerical value is the biggest is our max, whatever is the smallest is our min. In both of those examples, in fact, the first 3 examples, undefined wasn't an issue, but undefined points can be points of interest, as we saw here in this example with x minus 2 to the 2/3. It happened to be undefined at x equals 2. The original function, when we evaluate it now at x equals 2, we find that that is our smallest numerical value. That's our minimum at 0, and our maximum is 2.08, the cube root of 9. Okay. So first thing we're going to talk about is absolute max and min. That's the first thing that you're going to run into on your exam, is the absolute max and min. We then talked about Rolle's theorem and mean value theorem. Those are both existence theorems. So what you're going to do, be asked to do, is verify whether or not Rolle's theorem can be applied or not. So here we had an example with x to the 2/3. It is continuous, and the two endpoints do equal. That's one of the other requirements for Rolle's theorem. But it doesn't have a derivative at 0. Right? 0 is in that interval, so it's undefined there, so it's not differentiable there. So that one, we just say it doesn't apply, and then we're done. Here in this other example, we check the endpoints are equal. In fact, they're both 0 in this case. The function's continuous because it's a polynomial, and its derivative's a polynomial, so it does apply. And then the second part of the problem is find all those values that Rolle's theorem guarantees. Rolle's theorem guarantees that the derivative will be 0 someplace in that interval if these 3 conditions are met. And so we solved here using the quadratic formula. Mean value theorem says if it's continuous and differentiable, then there's a place where the slope of the tangent line is the same as the slope of the secant line. You can see that here in the visual picture. The secant line and the tangent line here are parallel. So again, in this example, we checked. It is continuous in the interval 1 to 4. Right? 0 is not part of the interval, so that's why it's okay. And likewise with its derivative. So it is continuous and differentiable, so mean value theorem does apply. So then we looked, when is the derivative equal to the slope of the secant line? And we compute that and find out our x value is approximately 1.86. And we then talked about increasing, decreasing, relative maxes and mins in our next topic. So you're going to be looking at problems a lot like this where you're going to need to find the derivative, figure out when it's 0 or undefined, use those values to test the derivative now to see when the derivative is positive or negative. If it's positive, then it's increasing on that interval, as was the case in this problem. If it's negative, it's decreasing on that interval. You could also be asked about relative max or min. So in the same problem, I just took and relabeled my sign chart, and here I see that it's increasing, and then it's decreasing, so that's a relative max. Okay. And then it's decreasing, and then increasing at 1, and so that is a relative min. All right, now as the result there known as the first derivative test. So once we have our sign chart, we can also talk about relative maxes or mins. So usually on the test, those will be separate problems. And in similar fashion, we talked about concavity and points of inflection. So those problems require us to find the second derivative, set the second derivative equal to 0, and then solve. Also check to see if it's undefined, because that could be a problem. This one, being a polynomial, didn't have that. So then we test the second derivative. When it's positive, we say the graph is concave up like a cup. If it's negative, the graph is concave down. And then places where concavity changes, whether it's positive to negative or negative to positive, doesn't matter. Those are called points of inflection. So we label those points to get our points of inflection. And we then moved into talking about optimization problems. And basically, you can kind of think of your optimization problems as being, usually you have to come up with a relationship, right? Here's an example where we had fencing. Instead, we decided we wanted to fence a barn here. In this case, we knew how much area we wanted to have. We were trying to find the dimensions in this example. So if you kind of look at the examples that we did here, this one is kind of a little more involved here with this minimizing time here, a little bit messier. Here we're cutting a box out. Here, of course, is the one we're doing a turn-in problem on. And so you can expect probably about 2 questions with optimization. You know, refer to some of the examples that we did, as well as what you did on your practice test as well. And then we talked about Newton's method. On the exam, you're going to be given a problem with Newton's method where it's going to ask you to put in several guesses, you know, the results from each of the guesses. Main thing I'm looking for is that you understand, you know, the process of how to set it up, right? It's the new guess is the previous guess minus the function evaluated there, divided by the derivative. Right. So I showed you, of course, how you can do that on a calculator and quickly get to the end. Again, just be careful when you're entering them in. If you run into an issue where you have the right process, but it's because of how the computer grades it, it's looking for you to round a slightly different way or something, and if that comes up as an issue, yeah, as long as you're showing me your work and I can see that you know how to set up Newton's method, what the function derivative are, kind of as we did here, right? X minus f of x divided by f prime of x, right? I can see the setup and the result. I will look at your work and correct that, if there's an issue with the computer and how it's grading it. So, but there'll be one question with Newton's method, and it'll be like what you have on your practice problems. The final topic that we talked about were limits at infinity. And so then you will have some questions where you're asked to compute limits at infinity. And basically, the process here is that we divide by, the largest power of x, to see what's left over. So expect to have a couple of limits as you go towards infinity, which of course turn out to be horizontal asymptotes. Okay, so you have your practice problems up on my math lab, so you can check those out. And then your test will be available next week. You can, again, go through the test 3 practice, and the last one or two of them, I think, are some limits at infinity. So here's an example with the limit going to infinity. So remember, we would divide both top and bottom by the largest power of x, which is x cubed, and then work that out. And here's what I was telling you again with Newton's method. So you're given a function, an initial guess, and then you want to fill out the values. So again, there may be an issue with rounding. If that's a problem, let me know. If it's marking some of them right, some of them wrong, let me know, and I can go in and fix that for you. And definitely on your test, I'll see your work, and I can update that for you. So I think that's everything. If you have questions, please contact me, reach out to me, and let me try to help you.